This is our second and final example for section 7.3 day 2. As you can see from the title here, we're going to solve a system of equations with infinitely many solutions. Now in the past we've just said, oh, it's infinite, and left it at that. But here we're actually going to get somewhat of a guideline for the types of solutions it's going to be. It's not that we can just pick any numbers that we want and call those solutions. So we're going to find out a way to represent an ordered triple that actually works in both, and then we could find multiple triples that work in both. Now the first thing that we're going to do, just because this section focuses a lot on matrices, we're just going to convert this to a matrix. So I've done so right down here. So we convert to that matrix, and we're going to use that and do some row operations with it on this next step. So here is that same matrix. One thing that will come into play for this one, and the reason that this is infinite solutions is because you'll notice that there are only two equations, but there are three variables. We still have x, y, z, but only two equations, and so there's not enough equations to fit the number of variables we have. That's going to be making a mismatch a little bit. So what we're going to do is still try to get this in reduced row echelon form, but it's just going to be ones down the diagonal here and here with zeros here and here. So we're just looking to make that little first part that's a square into the ones and zeros. But in this case, we're going to do that by our traditional method, which means we want to eliminate this 5 first. So if we want to eliminate the 5, let's use the first row, multiply that by -5, add it to row 2 to get a new row 2. So that's right there. Here's our description of it. It will look like this if we do the details. -5, 15, -10, and -90. Multiplying that row by -5. And then we add that to the second row. Which, if we put those together, we get 0, 2, 2, and -10. So we're going to replace that. We're going to use this as our new row 2, which is going to be right there. All right, now with this row, or with this new version of the matrix, what you might notice is that we have all even numbers in this second row now. This isn't one we've used all that often, but just to illustrate now, we can actually reduce those down. We can divide the whole row by 2, or think of it as multiply it by 1/2 and get a new row from that. We just are simplifying the numbers a little bit. So we would denote that is 1/2 row 2 is the new row 2, and so therefore my new version of this matrix is like that. And now we have ones going down the row, or going down the diagonal, which is nice. Now we've reached the end. We've gotten to the point where we're all the way down. Now let's start going back up, kind of like we did in the last example. So we're going to try to now eliminate the -3 by using this row. So for that case, what we'll do, I'll go to the next sheet first. So for that one, we are going to, let's get in focus here, we're going to do 3 times row 2 plus row 1 is the new row 1. All right, so that means 0, 3, 3, -15, plus 1, -3, 2 and 18, which will give us 1, 0, 5, and 3. And so we're going to replace that row with that information there. So here's what we have so far. We've got now this reduced row echelon form. This is kind of where we want to build our final piece of this problem. We've got this this identity matrix, this square identity matrix at the beginning, which means it's reduced row echelon form. Now we want to actually try to find some solutions that are going to work. So when a system has more variables and equations, it has infinite solutions, and we're going to go back to, we're going to take a look at what this means in terms of of equations at this point. So here is my matrix yet again. What I'm going to think about here is that maybe this is, let's rewrite this as an equation. So that means, make sure we got enough room up here, that means x plus 0y plus 5z equals 3. This second row means 0x plus 1y plus 1z equals negative 5. So those are our two equations. This is what we're talking about here. And so we want to represent each and every variable in this solution. Now we're going to notice that both of these equations involve z. And so when we talk about z, what I'd like to do is let's isolate the variables x and y so that we just have a way to somehow represent them to show what they are. So if I were to solve this for x, that would mean subtracting 5z from both sides, and that would mean x is equal to negative 5z plus 3. Then if I do the same kind of thing to this second equation, I subtract z over to the other side, that means that y is equal to negative z minus 5. So y is equal to this, x is equal to this, z is still just z. So what we're going to do then is talk about using this for x, this for y, and in order to triple, we're going to make what's called a general solution in this case. General solution for infinite answers. It's going to be an ordered triple. So I'm going to put some parentheses around here. Z is just going to be z. We also did find expressions for x and y. We don't actually have values for them at this point. But if we want to just call that x, we can put in place of x negative 5z plus 3. And then in place of y is negative z minus 5. So it's not an exact solution, but at least it only involves z, and so we could pretty easily pick a solution that actually works here. And that's going to be our last part to this problem, is to think about specific examples. Now, one specific example I have here, what I have going on is what if I picked z to be 1? Well, if I put 1 in for z, okay, that would be the first part of it. Then for the other ones, for the x and the y, I'm just simply plugging in 1 to these values. So negative 1 minus 5 is negative 6. That's where the y is coming from. And then I can put the 1 in here, negative 5 times 1 plus 3. That's going to be negative 2. And so that's our x value. So that's one example of a specific solution. If we wanted others, we could just pick other values for z. We really could pick anything we want. Maybe I pick 2, and if I pick 2, I plug it in, negative 2 minus 5. Okay, that is negative 7. And then over here, negative 5 times 2 plus 3, that will be negative 7. So there's another way I could pick those values and get something of a specific solution. It needs to work in the original, but if you have a specific solution and you think it might work, check it just to make sure. But again, these are specific solutions, possible solutions, and then this is a general solution. This is what it's going to look like anytime you're working with infinite solutions for this kind of system.